3.2 differentiability. That means the ability to have a derivative. So a function has a derivative as long as it is smooth and not vertical. So if a function looks like that, that means it's differentiable or has a derivative everywhere in its domain here. Okay, so as long as it's smooth and non-vertical, it has a derivative. So it's more interesting to look at where do derivatives not exist. So some examples. Alright, so this is my function. Don't ask me to get an equation for that function, but it has a bunch of points where it's not differentiable. Okay, so nice and smooth right here. This right here, that's called a cusp. So a cusp is when it's like a seagull. If the one side and then the other side, it approaches like vertical and then it goes vertical on the other side, that's called a cusp. So at a cusp, a derivative is not going to exist. Here's another one right here. That's a vertical tangent. So we learned back in algebra that it's undefined. The slope is undefined. So our derivative is undefined here because it's vertical. It's smooth, but it's vertical, so the derivative does not exist there. Any point of discontinuity, this is a jump discontinuity, but any point of discontinuity, the derivative is not going to exist. Okay, and then the last one here is a corner. So a corner is like when you connect one piecewise function with another piecewise function, maybe, or an absolute value parabola. It could generate a corner. And so all of those are where a function is not differentiable. Let's see. So, this is an exploration in the book. I'll just kind of pull it up here. So it talks about if something's differentiable, it has local linearity. Okay, so what that means is if you zoom in enough, it's going to become a line. So if you look at this curve, it's smooth. If I looked right at that and enlarged it, still kind of curving, enlarge it again, eventually inside that box is just going to be like a straight line. Okay, because it has local linearity. If I look at, this is what the book is doing, square root of, okay, absolute value of x, and if I graphed it, we know that's a v. If I zoom in, does it have a derivative? Well, it's got a derivative everywhere except for at 0. It doesn't matter how many times I zoom in, it's still going to be that corner there. Okay, so if I asked you where does the absolute value of x, where does the derivative exist, or where is it differentiable, you'd say everywhere except at 0. Now, what if we did the square root of x squared plus 0.0001. Okay, this is the example in the book. So I'm going to do a zoom standard. It looks like absolute value of x plus 1. So let's see if I zoom in. Okay, so it really does look like absolute value of x plus 1. But I'm going to zoom in a couple more times here. It looks like it's starting to flatten out a little bit. So eventually, unless the calculator dies, it's not a glitch on your screen. My calculator is not showing the graph anymore. Okay, so the point was, if you zoom in far enough, that one does have a derivative at 0 because it does have local linearity eventually. Your calculator, what it does to find a derivative is just, it picks 2 points right next to each other, really close to each other, but right next to each other, and then it finds the slope in between. So let's say I go back to absolute value of x. And I want to find, well, first of all, I'll graph it. Your calculator actually will give you the derivatives. So I can go to calculate derivative anywhere I want. So I'll pick it at like here, 3.3. The derivative is dy dx is 1. Slope is 1. Anywhere over here you're going to need a slope of 1. Anyone over here, if I find the derivative, it's going to have a slope of -1. So I could just type in -5 and it gives me -1. You don't have to move the cursor, you can just type it in and I can find the derivative of any point. Now what happens if I want to find the derivative at 0? I'm typing in 0 now. It gives you 0. Now why does it do that? Well, I thought we learned that, we learned that the derivative doesn't exist at 0. There's a corner there. Well, the way the calculator does it is, I said, it finds the slope at 2 points right next to each other. So if I zoom in enough, and maybe I'll just grab the 2 points of the calculator, it grabs just to the left, we'll call it like right there, and just to the right there, and it connects them and it finds the slope. Well, what's the slope of one to the left and the right? It is 0. So the calculator is wrong. The derivative does not exist at 0. It's actually undefined at 0. The calculator thinks it's 0 because it picked a point just to the left and just to the right and connected them. Okay, so there's some issues with the calculator, the way they've defined how to find the derivative on the calculator. What if I have x cubed and I wanted to find the derivative at 2? Okay, so we can find the derivative at 2 right up here. We could go through the process longhand and find if y equals x cubed, we could do x plus h cubed minus x cubed over h as h goes to 0, and eventually you're going to get 3x squared. That's what our derivative is going to be. Y prime is 3x squared if you went through all that algebra. Okay, so if I wanted to know y prime of 2, it would be 3 times 2 squared, which is 12. So the answer is 12. We did it analytically. Let's see what the calculator gives us. Calculate derivative at 2, and it gives us 12.000001. I don't know if I got the zeros right. Okay, so the calculator thinks it's 12 point a bunch of zeros 1. It's actually 12, so don't be the student that on a test uses the calculator to figure it out and does 12.0001. The answer is 12. So the calculator, when it grabbed 2 points right next to each other, it was almost exactly 12, but there are restrictions on how precise the calculator can be when evaluating derivatives. That's about it for 3.2, differentiability.